compoundings that aren't just annual. Today we're going to start on page 52 in your books. Now on page 52, if we look down to the bottom, we see some talks about our institutions and compounding beyond what we have our annual. For instance, most banks are going to do what they call quarterly compounding, where they compute our interest every quarter or 3 months instead of computing just annually. So what they do is they take that annual interest rate, let's say they offer 8%, and they're compounding it quarterly. So instead it's more like 4% to determine that quarterly growth factor. And again, we call the 8% a nominal interest rate or a yearly interest rate versus 2%, which is the quarterly interest rate. So if we see down at number 3, if we are compounding quarterly with a 5% interest rate, we would take that 5% divided up by 4. So really it's 1.25% as opposed to the total of 5 for the year. So then on page 53, if we see our pal Margaret investing $50,000 at 5% compounded quarterly, again, what she's going to have each month is instead of our, quarter or our annual interest rate, that 50,000, it's really being multiplied by 1.1025% to the T. In this case, that's 1 because it's been after 1 compounding. So that's coming out to be like 50,625. And then the next one we would say, okay, every 6 months. So that would be the 1.0125. It's been compounded twice. And then every 9 months, so that would be a third time. And we see this pattern continuing on and on and on, where if we have, like, for instance, the 1 year marker, it's been compounded officially. T would be 4 times, or like 4 years, that would end up actually being 16 times it's been compounded to the T years. So again, it's happening 4 times T. So if we actually looked at the formula, it's taking that 1.0125 and it's happening 4 times a year since it's happening officially every 3 months. And what we're seeing is that if we kind of took this out in an even further displacement, we see the 50,000. And again, if we think about, okay, we took that 5% interest rate divided by 4 to get the 1.25%, and then again to the 4T up top there. So this is kind of our setup we see eventually for our formula. And that's going to be our formula for compounding n times a year. And again, we'll talk about different types of n. And that formula now is changing this up. We're going to take our principal, 1 plus our rate value, our annual rate, divided by the number of compoundings. And then it's n times t for that. And we can solve, if we go back to the Margaret problem, just like we did with the other problems, for instance, the 5, for option 5, where we want to think about, okay, double time. Like if we want to see how long is it going to take to make $100,000 this time, and we started with the 50, and then this time we have 1 plus 0.05 divided by 4 to the 4 times t. Start by dividing by the principal value, right, the 50,000. So we have 2, and we know inside here this becomes 1.0125 to the 4t. And if we take the common log of both sides here, just like before, we are able to write now that exponent out front. So be careful, we have the 4t out front, and then we still have log of 1.0125. And then when we divide this over, officially the 4 and the log are going to be divided over. So when we type this in the calculator, you want to be very careful that you have log of 2 in the numerator, and then it's 4 and the log of 1.0125 needs to both be in the denominator. So be careful how you type this in the calculator, especially if you don't have the fractions. You would want to make sure you have log of 2 and then divided by parentheses, since we have that 4 with the log of 1.0125, and we want to make sure that that's calculated together in the denominator. And we end up getting 13.95 years approximately it will take. All right, so what we see here is that if it's being compounded quarterly, if we compare this back to what we had before, the annual we calculated in the previous lesson took about 15 years. And this is only taking about 14 years. So what we're seeing is that there is a little bit of time saved based on having more compoundings. It's taking about 1 year less to double that money. So that can help us out on those. Now, officially, we can compound, again, using this formula, more than even just quarterly, right? We have the annual rate where, again, our n is 1. So that's where we kind of can get away with just doing 1 plus r to the t because our n value is 1. So that changes things. Quarterly, we have 4 times a year. So again, that's going to change things up. We would take that r divided by 4, and then the nt, so 4 would go up. Monthly, I'm going to take this out here. Our monthly, that's 12 times a year, right? There's 12 months in a year, so it would compound. So we'd have p and then 1 plus r over 12 to the 12t. And then we could even, I mean, there's more than this, but, daily would be 365 times a year. 1 plus r, 365 to the 365t. So we see a bunch of different, and again, you might see semi-annually, you see semi-quarterly. They might just tell you straight up how many times you're compounding for that n value. And what we kind of see over the course of with money, as our rate decreases, as we get a smaller rate, but with more compounding, it's going to bring that rate down. But overall, our money is going to go up with more compounding. So even though that rate looks like it's shrinking, the overall money we're getting kind of increases on that. All right. Now, what we're going to notice then is what happens when these compoundings kind of take a turn and they start going, right? And so if we consider an initial investment of $1, and let's say we somehow got an interest rate of 100%. So R is 1. And we're taking it to the t power, so this would be 1 year. So basically what our formula is 1 plus 1. Again, we have over this x, depending on our compoundings, to the x times t, which again is 1 here. So each time we plug this in and we see we have the 1. This time if our rate is, we'd have 1 over 10 because we're compounding to the 10 times t. In this case, again, t is 1. And then we would have 100. So we're taking that compounding 100 times. So we would do 100 up here. So we see this pattern and what's happening. Okay, so this is essentially our x each time. Well, if we take our calculators and we look at the table of this, right? We take 1 plus 1 divided by our number of compoundings and then to that x power. Okay, and we look at our table. What we could do is we could set up our table to be independent, where we can start this and ask and just start typing in these different values from the chart. So we look here, we have 1, 10, 100, and then 1,000. And then we look at 10,000. And as we start seeing here, each time these values are coming infinitely close to a number, right? In particular, it's coming really close to 2.7183. So the balance after a year appears to be approaching $2.71, right? Or even more if we look at that, right? Now, this is what we call the letter E, right? We've talked in math land a ton about our pal pi, right? Your calculator has the pi button. It stores it in here. We know that that's 3.14. But that also is going to be another math constant that we call E. And E is also stored on your calculator. It's it's Euler's number. It's the lesser known value of 2.718. And what can happen with this is that we are going to see that is going to lead us into part 3 here, where we have continuously compounding formula. So what happens if we are more than just, even daily on our compoundings? What is going to happen here? Well, we are going to have what we call continuously compounding. And that formula is a little different than our others. Okay, that formula is what we call the PERT formula, right? P times E to the RT power. And we see with PERT, again, we have yearly, quarterly, and then we can even assume 365 days in a year, what it would be if we typed in that principal amount for each of these answers. So 50,000 with that 5% rate, we could see after 20 years that it's kind of giving us the daily. Well, what happens if it's continuously? So we would take that $50,000 initial interest rate, and then you would have E to the rate, which was 0.05, times T, which is 20 years. And we see that 135,914. So not crazy more than daily, but again, there is that idea then of our continuously compounding. And if we look at page 56 then, to go to example 3, we can see how this is even used also with depreciation, right? We've talked a little bit about depreciation before. So if we are continuously depreciating, so you're going to see this word continuously, that's key that we want to be using the PERT formula. And if we have an initial cost of $10,000 and it's depreciating at a rate of 17%, we want to know what's it going to be worth after 15 years. So what's the amount after, in this case, time is 15 years. Well, going to take that initial amount and then E to that R value, this time with depreciation. For the PERT formula, you plug it in as a negative, and then the 15th power. We see on this one that it's going to come out to be about $780.81. So over time, that's really taking quite a hit when you're depreciating continuously as well. Now, how long is it going to take for the boat to reach half of its value? Well, we have 5,000 as that initial amount. We have 10,000, or sorry, is the amount we're looking for. And then we have 10,000 was that initial cost. So if we divide this time by 10,000, left-hand side becomes 1/2. And if we are going to solve then, we use the common log a lot for our other bases, or base 10 is what undoes that. The natural log is actually going to undo our base E. So what we see here is those can cancel out if you take what we call the natural log, ln. So if I ln both sides, this is going to cancel out my base E. So I have ln of 1/2 equals negative 0.17 t. And if I take the natural log of 1/2, divide it by negative 0.17, I get my time to be about 4.077 years. About 4.1 years, a little over a year, or 4 years, excuse me, to get that time to depreciate. And we will see much more with these as well. If with these exponential decays and whatnot. Thanks everyone for watching. We will work more with all types of compounding and continuously in class.